thanks to the organizers. I have to approve the live stream. Thanks to the organizers for the invitation to speak, and thank you all for coming. So I'm going to speak about some joint work with Ilya Kavovich, Joseph Marr, and Catherine Pfaff, where the topic is random walks and out of N. So, I'm not going to, I like to hit a couple of punchlines, but I'm not going to rush through anything. So please feel free to stop me along the way and ask any questions you'd like. I want to give more of the idea of what's going on than of technical details. Okay, so let's get started. So let's just say what the setup is. So we'll be interested in the outer automorphism group of a rank N free group. So here and throughout the talk, N will be at least 3. So this is the automorphism group of a free group modulo the inner automorphisms. And so we're going to be interested in it in terms of its action on a particular space. That space is called outer space. So it's denoted CV for Kohler and Vogtman, who introduced it. So one thing I will not do in this talk is I will not dwell on the definitions. I'm going to give some intuition for what this space is and what the action is. So points in this space are what are called marked metric graphs. So I'll tell you what that means. So here's a picture of one. So a graph is a graph. A metric graph is that we've assigned positive lengths to the edges. And to be marked simply means we have some fixed isomorphism from its fundamental group to the free group we're interested in. Okay. So out is out of N act on the space. It acts on the space by just changing the marking. So if you're familiar with the Teichmüller space situation mapping class group, it's totally analogous. Okay, so we want to be interested, we will be interested in the boundary of this space, in the boundary of outer space. And one way of thinking about how to attach a boundary to the space of marked metric graphs is to think, instead of the graphs themselves, to think about the universal covers. So the universal cover of a graph is a tree. And since we have a fixed identification with the free group acts on the tree. So these are actions on the universal covers of these graphs, which are actions, so free actions on simplicial trees. Okay. So how do you attach a boundary to such objects? So, using ideas, using lots of good ideas of people that came before, one way of thinking about how to attach a boundary to the space of actions on a space of free simplicial actions on trees. So let's draw it this way. So we'll attach a boundary. So what we should do is we should think what happens as these actions degenerate. If you take a sequence of actions with no accumulation points in outer space, what we could do is take a rescale limit in the usual sense and extract from that an action on an R tree. So the points in the boundary, the way we attach points in the boundary is to think about rescale limits. And what we get in the end are actions on R trees up to scale. Okay. And so those R trees we want to think about as living at the boundary of outer space. Okay. So there's a lot one can say about what types of R trees. So maybe for the purposes of this discussion, what is an R tree? A connected zero hyperbolic space. And so lots is known, a lot is known about what are the types of R trees that lie at the boundary of outer space. But for us, it's not going to be so important. It's important to the general theory, but not to this talk, when I want to sort of give more intuition. What I want to do right away before we go into more details about what the structure is here, I want to ask the following simple question that's going to motivate the talk and motivate the paper that we wrote. So the question is the following. What does a typical tree, T, R tree, in the boundary of outer space look like? So that's the question that's going to motivate the talk. So in a little bit, I'll backtrack and talk about the corresponding situation in the mapping class group. So I think probably people have, maybe it's more common to think about the mapping class group and motivation coming from that setting. So we'll do that in a little bit. But for right now, this is the question, right? So I have this space of R trees that lies at the boundary of this space that out of N acts on, and I want to know what a typical one looks like. Okay, so of course I need to give you more precise definitions, right? I need to tell you, first of all, what does it mean? What do I mean by look like? So call that point A. We'll come back to that. And then I also need to tell you what I mean by typical. Okay, so these are 2 points we'll now address to sort of make this question more rigorous. Okay, so let's get started with item A. What do I mean by look like? So maybe the first thing we can talk about is T is a tree. Okay. So every point in the tree separates the tree. So for all points in the tree, T minus the point is disconnected. Okay. So maybe one of the most basic invariants I could think about is how many connected components there are, how many connected complementary components there are to a point, right? So I'll call that the degree of a point. It's simply the number of connected components of the complement. How to write that? Number of elements in pi naught of T minus B. So I'll call a point a branch point. If the degree is at least 3, that's where you actually see branching in the tree. And I'll call a tree trivalent if all branch points have degree 3. Yep. So that's the first property of a tree I'll be interested in. What are the degrees of the branch points of a typical tree? Okay. So that's something like very, very concrete, very, very topological about the tree. Another condition that I'll be interested in is more about the question of like where the tree comes from. So I think there's one very basic construction of R trees, group actions on R trees. So this is about how the tree arises. So how the tree arises. So here's one way of constructing an action in an R tree. So let C be a 2 complex with the fundamental group identified with the free group of rank N, and with coming equipped with a measured foliation. Okay. So 2 complex with a measured foliation. So what happens then is, of course, the fundamental group, which is we've identified with the free group, acts on the universal cover of the 2 complex. And I could take the leaf space of the corresponding measured foliation. So if I collapse the leaves of the measured foliation in a particular way using the transverse measure, what I get is an R tree. So I think this picture is probably people have seen before. So, right. So maybe in the universal cover of the 2 complex, I have a singular point that looks like this. So I've drawn a picture that I guess looks like a surface picture. And then what is the locally, what is the leaf space of this picture? That tripod right there. Right. So this is sort of a general procedure one can do is lift a measured foliation on a 2 complex, look at the leaf space and obtain a tree. And since there was an action on the universal cover that permutes the leaves, there's an action on this tree. Okay. So let's call a tree. So call a tree, right, really an action of the free group on a tree, geometric, if it comes from this construction. Okay. Maybe I want to point out that if you're used to thinking about the surface group case, it's an important result that all the relevant actions of surface groups on R trees come from measured foliations on the surface, and so they're all geometric. Okay, so in the surface case, if you were to think about the surface case, what we can think about is all the actions on the R trees satisfying certain properties are geometric. What we're saying here is that if you move over to the free group setting, that becomes a special property, being dual to a measured foliation on a 2 complex. Okay. Great. Are there any questions so far? Just these are the 2 properties that I'm going to be interested in. These are my 2 rigorous ways of making rigorous what I mean by what does a tree look like. It's the branching data and sort of where the tree comes from, how the tree arises. Okay, if not, now I have to tell you what do I mean by a typical tree. So here, I mean the measure coming from a hitting measure of a random walk. So I know Giulio's giving a mini course on random walks. I'm going to keep things as basic as possible for this talk. Right? I'm not so interested. I'm only interested in the simplest possible random walks using the simplest possible measures for this talk. So let me describe what I mean. So let's fix a symmetric generating set, a symmetric finite generating set. I'm going to call it S for the group I'm interested in, which is out of n. And I'm going to use the symmetric generating set to generate a random walk. So we'll let Gn be the increments of the random walk, be, let's say, uniformly chosen, random elements from our generating set that are independent for each n. Okay. So these are our increments, and then we could form a sample path which are just the locations of the random walker at step n, is obtained by concatenating our increments. Okay. Right, so the way of thinking about this is, if I'm interested where the random walker is at the nth step, I look where they are at the nth minus 1 step, and then multiply my nth increment. Right. So if I were to form the Cayley graph with this symmetric generating set, this is a simple random walk on that Cayley graph, where at any instant I'm someplace in the Cayley graph, and I flip a coin to decide which edge to go through next, multiplying on the right. So this is my notion of random walk that I'm going to use on my group. So then what I do is, let me just to draw the picture, right? I have outer space. Let's fix some base point x. Okay. And I look at the image of the sample path. You're looking at translates of x. So I'll look at the sample path, Wn of x, which in this picture will be some sequence of points in outer space. Okay. So maybe I don't want to dwell on this either, especially because there's been a mini course on random walks, right? So, and then I'll denote we'll denote by p the measure on the path space. Okay. So I think Julie has been talking about Poisson boundary, and in this case we have the following theorem that's due to, so I'll attribute it to Horbez and Namazi, Pettit, Reynolds. That in this case, in this situation, almost every sample path converges to a point in the boundary of outer space. Okay. So really, this is like the starting point for our question. So what do we have now? Now we can define, ooh, just lost my space in my notes. Right, once we have the fact that sample paths converge, what can we do is we could define a hitting measure, and we could talk about typical trees with respect to that hitting measure. Right, so now define nu to be the associated hitting measure. Right, so like nu of some set in the boundary of outer space is just the probability that a sample path of the random walk limits to a point in that set. Okay, so that's maybe the background. Here's the theorem that I wanted to talk about. So this is the theorem. This is joint with Kavovich, Mar, Pfaff, myself. Gives you more information about a typical point in the boundary. So a new typical tree, T, in the boundary of outer space is free. So this is a nice fact to know, but it's not so deep. So what I mean by that is these are all actions. So these trees all come with actions of out of n. With all these trees all come with free group actions. And typically the tree you see, the action is free. Right? So free actions on trees. They are trivalent. Okay. And they are non-geometric. Non-geometric means not geometric. They do not come from a foliation, a measured foliation on a 2 complex. Okay, so I think there's an interesting story here, an interesting connection to the mapping class group case, which is I want to focus on for a while. Okay, and maybe I want to point out directly at the outset that this trivalent condition is exactly like one sees in the surface case, exactly like the surface case. So the surface case is due to Gadra and Mar. So I'm going to talk extensively about it in a few minutes. Okay, so say it again, the trees being trivalent is exactly like in the surface case, but being non-geometric is the exact opposite of the surface case. So I'll say exact opposite of the surface. So I think there's something interesting happening here, and then the theorem, one end of it is exactly what you predict if you understand, what's happening in the corresponding Teichmuller space picture. And on the other side, the trees being non-geometric, saying that none of them arise as measured foliations on 2 complexes is exactly the opposite, because of course the boundary of Teichmuller space, they're all measured foliations on the surface itself. So that's what I mean in the sense that it's opposite. Okay. Great. So let me just maybe remind you, do the translating for you. What happens in the closed surface case? So the closed surface case. There, one is considering the mapping class group action on Teichmuller space, right, where the boundary of Teichmuller space is PML. So there, typical sample path converges to a point in the Thurston boundary, which is the space of projective measured laminations. And what's the corresponding statement? The corresponding statement is if the complementary regions of the lamination are triangles. That's the way of translating from the tree picture to the measured foliation and measured lamination picture. So typically, with respect to the hitting measure, the measured laminations, the complementary regions are all triangles. So are all triangles. So the process of going from the lamination to the trees, collapsing the complementary triangles into the tripod picture. Okay, so really the rest of the talk is going to be about giving an outline of what Gadra and Mar prove in the surface case, which I think will set our expectations and tell us sort of what we should be doing, and then explain to you why when you move to understand the corresponding picture in outer space, why, you know, a solid half of their setup fails, and then what you need to do to overcome that in the setting of outer space and in the free group setting. So that's the goal for the rest of the talk. Before we get started, any questions before I move on? Okay, right. So really our goal is to explain the mapping class group setup to highlight the difference with what happens in outer space. So let's now talk about random laminations in PML. And this is, you know, really my interpretation of Godger and Mars paper. And I'm gonna write it in 3 steps. My interpretation of what they do in 3 steps. So step 1. So this point, we've now transitioned, and we're going to talk about mapping class groups action on Teichmuller space in very broad strokes, and explain what they do and why it works, maybe more important. So first, they prove that a random Teichmuller array is what I call principally recurrent. Okay, so this is just what I call it, but it's, you know, it's essentially contained in what they prove. So let me say what that means. So first, let's fix what I'll call a principal pseudo-Nassov phi in the mapping class group. So what does this mean? It has an axis, A in Teichmuller space. So the pseudo-Nassov translates along its axis. And A, to be principal, is contained in what's called the principal stratum of the space of quadratic differentials. I don't want to get into technical details. Let me tell you what that means for us. What does it mean for us that it's contained in the principal stratum? So first of all, it means that its endpoints are trivalent. So remember, if you remember what the construction of Teichmuller geodesics, you have a quadratic differential and it has a measured horizontal and a vertical measured foliations. Here I'm saying both those measured foliations are trivalent in the sense that they're dual trees, have degree 3 branching, or if you thought about them in terms of laminations, it's just the complementary triangles condition again. And the other important condition is that being in the principal stratum is open. So this is an open condition. So, you know, you might ask what I mean by open. Technically, I'm referring to the topology on the space of quadratic differentials, but let's just take it intuitively that being in this principal stratum is open, so any other bi-infinite geodesic that's close enough to A, meaning fellow travels it for a long time, is also in the principal stratum, and hence has the trivalent singularity condition for its endpoints. Okay, so far this is just some setup. So it's known such pseudo-Nassovs exist. Okay, so now what does it mean to be principally recurrent? So a geodesic ray, let's say geodesic ray gamma, is phi recurrent, where phi is one of these principal pseudo-Nassovs, if for all numbers L, so all big numbers L, gamma fellow travels a translative A for distance at least L. Okay. So maybe somewhat of a funny property. So I have my ray gamma, and then you give me some huge number L, 10,000. And what I do is I go far enough out along my ray, and then I see that eventually gamma will fellow travel a translative A for a distance at least L. So by translative A, I just mean under the mapping class group action. Right, so if the translate is GA, then of course that's the Teichmuller axis for the conjugate of phi by G. This question makes sense? Or this question, does this definition make sense? Okay, so what's the lemma? This is attributed to Gadra and Marr, although they're assembling work of others, is that random rays are principally recurrent. Okay. Cool. So that's step one, random rays are principally recurrent. And here, of course, I mean, you're sampling points in the boundary of Teichmuller space and the Thurston boundary with respect to your hitting measure, and then you're taking a ray from a base point with to that random point in the appropriate sense. That's step one. Random rays are principally recurrent. That's like the tagline for step one. Step two maybe is like just totally trivial in this case, or if you know something about Teichmuller space, you'll think it's trivial. It's just fellow traveling in this case, fellow traveling. So that means, I didn't tell you how close is fellow traveling. It just means it stays within uniformly bounded distance for longer and longer times. But in this setting, fellow traveling will imply like very close fellow traveling. So as close as I want, very close fellow traveling. In this particular setting where I'm fellow traveling the translates of axes of Pseudo-Anosovs. So that's step two. That's just me saying in this picture, I don't have to redraw it. When I say gamma fellow travels the translate, I can mean like I could also fix an epsilon initially, epsilon fellow travel. Cool. And then step three is essentially, I've already said it, it's just the principal stratum is open. The principal stratum is open and invariant. Okay, so what's the point? The point is I have my fixed, I chose this random point here, and then I drew a geodesic to it. Gadra Marr tells me that it fellow travels GA for longer and longer times. Step two says it fellow travels as close as I want. But I know each of these GAs is in the principal stratum. Okay. And since gamma is fellow traveling them for as close and as long as I want, they have to be in the principal stratum as well. And that principal stratum condition is exactly implying that the, I don't know what I want to call it, the endpoint in PML is trivalent. I'll just say is trivalent. Cool. I think it's, I don't know, I think it's like a satisfying reason that I have that typical laminations are trivial. I keep saying that, and I mean with respect to the hitting measure. I mean, if you, for instance, think about a different measure, like the Thurston measure, then was known earlier for other reasons. So if you know all of these things, I'm always talking about the hitting measure for it. Okay, questions before we go back to outer space? I'm ready to go back to outer space. I'm happy to be teaching in person again. It's not, otherwise, I was getting used to like this kind of silence. So it's nice to be back in the question. Okay, back to outer space. So first of all, let's just try to like copy the steps, right? That's, improve something about out of fin or out of space. Just first try to copy the mapping class group setting and then see where you get stuck. So let's do that. So step one, and hopefully I'll try to convince you that like you really, really get stuck. Okay, so which means that like what you have to do to actually overcome being stuck is worthwhile. Okay, so step one is suppose phi, this is now an outer automorphism. I could also zoom in. Is that what you prefer? I mean, I can rotate the iPad, of course. I'm happy to do whatever the preference is. Yeah, okay, so suppose now, so phi is a fully irreducible outer automorphism. Julia is very savvy when it comes to technology. So now we're back in outer space. We're back in outer thing. So let's say is a principal outer automorphism. I don't even want to say it. It's principal with geodesic axis A in outer space. Okay, so I'm obviously not really telling you what any of this means yet. We'll put on the properties as we go along. Right now, what I want you to think is I have the same sort of setup. I have a particular type of element in out of n that has a geodesic axis, this time in outer space. Okay, so again, I could define being principally recurrent in exactly the same way. Okay. So here's the proposition. So everything that all these things are contained in this paper with Ilya and Catherine and Joseph. So same thing. A random folding. I'll tell you what folding means in a second. Geodesic. I usually denote that G of t is phi recurrent. Okay, so the picture is the same. So here I have, I pick my random point, my random tree in the boundary of outer space. And G of t is the random geodesic to that point. So this is like a one parameter. You should think of it as a one parameter family of graphs. That's why it's being denoted G of t, but it's a geodesic. Okay. Then just as before, we have this fact that for longer and longer amounts of time, it will fellow travel a translated geodesic. Okay, so in some sense, the proposition totally mimics the Teichmüller space setting. I will say this requires some amount of work. One needs to promote what's known some sort of fellow traveling in the free factor graph to fellow traveling in outer space, and it required establishing some sort of bounded geodesic image property for these axes. But it's not the point of the talk. From the point of view of the talk, this is the step that works just like it should work, just like in the mapping class group setting. That I have this recurrence for random geodesics. Okay, so that was step one. And step one is supposed to be exactly the same. So step two is supposed to be phi recurrent. So recurring to one of these axes is supposed to imply very close fellow traveling. However, again, one can prove this, except there's an issue. There's an issue at the outset, and that's that axes of these types of automorphisms, fully irreducible automorphisms, are not unique. And so here one runs into a little bit of a road bump in proving this implication. However, it's not so hard, and it involves what it means to be principal. So principal implies that phi has what's called the lone axis property. So it has a unique axis. And then with that observation, the proof is just like before. Okay. So again, you should be thinking this step, there's a little bit of a complication, but it's not so bad. Okay. But then step three doesn't work at all. So I'll just put a bunch of red question marks. So remember, if we go back to the surface group setting, that used openness of the principal stratum. So this principal stratum is in the space of quadratic differentials, which is the cotangent bundle of Teichmüller space. or essentially have some open invariant set in the cotangent bundle of type in outer space. And at least a priori, there's like no similar structure in outer space. Outer space is in the manifold. There's no obvious cotangent bundle. There's no obvious meaning for openness. So sort of this fact that we used before, using sort of complex analytic structure of type Euler space is just not around in the setting. So one needs something totally different to say how sort of trivalent singularities for one folding path is going to force it on another nearby geodesic folding path. Okay, so there's a new idea that's necessary. And that's where we'll go next. Before we do that, any questions?
Sorry, when you say fellow travel, do you mean like bounded neighborhood by a constant or some sort of
yeah, so when I initially say fellow traveling, I just mean like there's some kind of uniform fellow traveling, you know, there's some number like 10,000 that you're given at the start of the problem, and then you 10,000 fellow travel. And then what I was saying in step 3 is doing that infinitely often for longer and longer will imply like very close fellow traveling, where the quantifiers are such that, you know, for any epsilon in L, you'll epsilon fellow travel for length L.
Okay.
Yeah. The reason is like intuitively simple, right? You're going to fellow travel for longer and longer and longer and longer. The translate of one thing, but then if you just, you know, translate the whole picture back, you have one invariant axis that you're fellow traveling for longer and longer and longer and longer. And if you weren't getting very, very close, you would limit to an axis that's distinct from the original, which if there's only one axis, you use the contraction. It's a pretty soft argument.
Okay, thank you.
Yeah. Cool. Okay. Anything else? Okay, so what's the new idea? I say new, but the paper is like 2 years old. So yeah, so it's eventually, should I say it? I have to say it a bunch of times. Yeah, so it's just, you know, I'll just write new idea. Okay, so I just have to say a little bit more about the type of geodesic that I'm talking about. So what are these geodesics? So there's the definition, a geodesic ray. So I always write this as G sub T, like a one parameter family of graphs, is a folding ray. I want to give kind of a intuitive definition with a picture. So this array, the graphs, come equipped with maps from one to the other. So if there are folding maps, and folding maps are exactly what you think they should be. So there's this map from the graph at time S to the graph at time T that is respecting the markings that come from the fact that this is a path in outer space, such that for T minus S small, all this map is doing is like taking two edges that start at a vertex and folding them together. So the picture might be something like, this is at least true for small, changes in time. So here's what the graph looks like at time S. And then what's going to happen is that these points in those edges are going to get identified so that at time T kind of gets zipped up a little bit. So that's what folding maps do locally for small times. Of course, that's like a description of what happens for small time. And then as you let time grow, you see certain events where vertices collapse into edges or collapse into each other. And that's where the topology of the graph changes. But this is what's happening at a local level. This is a way of moving around in outer space with these folding maps. Okay. So this essentially tells us how to start with a point in outer space, the boundary of outer space, and build a folding map to it. So let's just say it this way. For typical points in the boundary of outer space, which we should think of as trees, there exists a folding ray, one of these geodesic folding rays, such that if I think about that one parameter family of graphs, well, maybe first I take the universal cover, and that sequence converges as a, say, a rescale limit to the tree T in outer space union its boundary. So all I'm saying here is you take a typical tree in the boundary of outer space, and there's a way of getting that tree as a limit of one of these folding paths. So a good guess would be, if I want to study the tree, why don't I study the graphs that I see along the sequence? That would be a good guess. So maybe the idea or the guess is that the branching of the tree T, like the degree of the branch points, is determined by that of G of T. And so G of T are just graphs in outer space. They're just graphs. You could look at each one of the vertices and look at the degree. Okay, so might be something you guess. Right? So this turns out to be too naive for a number of reasons. So I just want to show one issue that could arise. So here's one issue. So it's an idea, but here's an issue with that idea. The issue is in a picture. So I'm going to draw a portion of the tree. I'm not drawing the whole tree, just a portion of the tree. So pretend you see this picture. Okay, so that's like a picture in, I'm sorry, that's like a picture in these G sub T's. Okay, what do I mean? Like G sub T is an evolving family, a one parameter family of graphs. And you imagine in that picture, this is what you see at some time. Okay. And imagine that as you let time go on, these edges are folding into each other. Right, so, as time elapses, these two branches are getting zipped up together. Okay. And let's suppose for all finite time, they never get completely identified. Right? So every 2 points in the interior are identified after some amount of time, but the whole branches are not identified in the interior. So these two vertices right here, maybe I should have drawn them in blue because they're not getting identified. For any time t are not identified. But of course, if points arbitrarily closer to them are identified, then in the limit, they do get identified. And what does one see in the limit? One sees a picture that looks like this. So, even without understanding the structure of outer space or structure of the boundary or anything like that, we see a big problem here, right? Because in this local picture, I have a vertex of valence 1, 2, 3, 4, 5, degree 5, right? However, in every approximate picture, every vertex has degree 3. Does that make sense as a problem? Like, I want to understand the degrees of branch points of these trees. I know I can approximate them using these folding paths, but this picture illustrates that, just approximating it with a folding path isn't going to accurately reflect what's happening with branch points. Cool. Of course, like when I say I didn't draw the whole picture, of course, like there's lots of stuff happening up there. There's lots of stuff. There's lots of branching and stuff. But the branching at the blue thing in the limit is different than anything I see in the approximates. So that's a real problem. Fortunately, it's like very easy to put your finger on why that's happening. So let's say why that's happening. In the approximates, I could build the following path. So this is a path P. So that I'm using path in multiple languages. So the whole thing's a folding path, and now I'm taking like an honest just path in that graph. Cool. What's happening to P along the folding path? Well, if I fold for a little bit, at some intermediate time, if I fold, say, for a couple of minutes, I see that picture where this part I folded up, right? And so I can tighten it. I can tighten it just by removing the part that backtracked. But at the next instant, I start folding it again. What I have when this picture develops is I have a path that is folded forever, right? And at every instant, I fold it, I tighten it, and it still folds some more. It never stops folding. Okay, that is exactly the problem. Okay, so let's define a family of paths that defines away the problem. And here's the definition. Okay, say this one parameter family of paths is eventually legalizing. Is that what I call it? Yeah. So a legal path never gets folded. That's where the term legal comes from. If for any path P naught in some initial graph G naught, some initial time, what I'm going to write, it just means there exists some time such that after that time, the path doesn't get folded anymore. So let me write it. There exists a time greater than T naught such that if I let PT be the path I get at time T by folding and then pulling it tight, so you could write it like this. So I take the image of that path using my folding maps, and then I pull it tight. So this means pull tight. This is never folded again. Never, maybe I'll just say no longer folded. And for those, it means it becomes legal. That's why the name of the path is eventually legalizing. Okay, so all I did is I defined away this problem. I saw this picture, I saw this path that's always getting folded. It causes me to get confused about what's happening to branch points at infinity. And I said, well, it's because I'm just folding something forever and it gets collapsed at the last instant. Let's just make sure that never happens by defining it away. A folding path is eventually legalizing. As if every path, you let the path evolve under the folding maps and it eventually straightens out and it never folds anymore. Okay. What's the proposition? Is basically this fixes the problem. Okay. If G of T is eventually legalizing, and sometimes trivalent, what that means is I just have this family of folding paths. Let's pretend there are times where the graph has only degree 3 vertices. I mean, it's just a graph. Maybe there are instances where it has degree 3 vertices. So this is eventually legalizing folding path with G of T converging to some T in the boundary of outer space. Then T is trivalent. All I'm saying here is suppose I have this point at infinity, I take one of these folding paths that happens to be eventually legalizing, then the branch points at T are accurately reflected by the branch points of the graph. And if the graph is trivalent, into the future at certain times, that forces all of the branch points to have degree 3. Hopefully that's somewhat of a intuitive explanation. Basically, it's we ruled out the problem, and once you rule that out, you could say that the branch points of the tree are accurately reflected in what happens in the approximates. And then maybe what's the point is that, so we already said that random folding rays are principally recurrent. Okay. The last proposition is that principally recurrent, or maybe I called it phi recurrent. I chose a principal automorphism and I called it phi recurrent. Folding rays are eventually legalized. And then if we put together the propositions I've stated before, we have proven that a typical tree in outer space as all of its branch points have degree 3. So maybe just one more time in words. You take a typical point in the boundary of outer space. You could build a folding ray to it. That folding ray will fellow travel translates of an axis of a principal automorphism for longer and longer and longer. Then when that's the case, that folding ray becomes eventually legalizing. So that's maybe the technical heart of the paper. It has something to do with what the principal what it means to be the principal automorphism and what very close fellow traveling outer space forces. But then once you're eventually legalizing, then you've gotten rid of all the problems. You could just read off the branching data from the approximate graphs. So should I stop there, or do I don't know how much time I have.
You have until 1. You can I don't know.
Yeah, okay. I actually wrote down a list of two open questions that I like. So I'll just share my open questions, and then someone can tell me if they have an idea for how to answer them. So 2 questions. So the first one I didn't put too much thought into. The second one I put a lot of thought into. So, okay. So what did we just prove? Or we saw the proof that if I take a random tree T, the action is free, trivalent, and non-geometric. So, just using some out of n theory, this implies that the number of orbits of branch points. So I know all my branch points are degree 3. Okay. It turns out there's finitely many orbits of branch points, and the number of them, has to be at least 1, and has to be no more than 2n minus 3. That's the most number of branch points it can have. Now, if I was in the surface group world, I would know exactly how many branch points it has, because the number of branch points is exactly the number of singularities of a measured foliation. And if I have a measured foliation and I know it's 3-prong singularities, I know how many singularities there are by whatever, Gauss-Bonnet or Poincare-Hopf or whatever. Okay. I don't have that in the free group setting. However, I'm 100% sure the upper bound is what happens. So, prove, the open question is prove that for a typical tree in outer space, the number of orbits of branch points is exactly 2n minus 3. Probably saying that in a very muddled way. Prove equality. Typically. Prove,
so where does your sense of certainty come from?
Yeah, that's a good question. How can you lose branch points? There's only one way to lose branch points. It's when you evolve your graph, you have your graph you have a graph and it has degree 3. All of its vertices have degree 3, and it represents a point in out of n. You know how many vertices there are. There are 2n minus 2 vertices, for sure. That again is an Euler characteristic count. And then you start folding, okay? And you have to be folding something. So one of those vertices goes away. In order for an additional vertex to go away in the limit, your folding path has to, for some reason, collide vertices infinitely often. Like you're doing this folding path. Typically, when you do a folding path, a vertex, when you fold, gets folded into the interior of an edge. In order to lose vertices, it actually has to be, the lengths of the edges have to be perfectly proportioned with respect to each other so that 2 vertices collide. And the vertices collide infinitely often. Like 2 vertices collide and then you fold, you get new vertices and they collide again. I mean, how can that happen? If I was randomly folding, if I was randomly taking edge lengths and folding graphs together, you don't collide vertices.
There might be a reason to think that should actually happen, Sam. So the reason is because every time you fold the two edges exactly, then you have these four things, and then you have choices. These guys can fold together or some other way.
Yep.
So there is an extra choice you get. So most of the growth comes from, in fact, this phenomenon that you have this extra choice. So that could
No,
be
no, no.
in
The
fact-
growth. You mean like the growth of like automorphisms? Like I was thinking
Right,
about building.
right.
No. You could ask a different question.
No, I understand it's a different question. I'm just saying.
But no,
that,
no.
you
I'm
know,
saying.
Yeah.
I think we also proved that if you take a typical fully reducible, its stable trees are trivalent. And I think in that case, when you are doing a random walk and asking about the stable trees, I don't make a conjecture there. And I think your intuition, I don't know, my guess is that your intuition,
I mean, like, no, random walks are kind of special anyway. But if you pick like some analog of the Patterson-Sullivan measure or some other kind of thing, then
Yeah.
and then you go in that direction, then this infinitely many times edges collide. It will be in fact typical.
no,
Like
no,
in
no, but why would you be assigning the same like arithmetic measures to different edges? Like why wouldn't two edges just initially get some measure so that the lengths aren't rationally related and then
Well, it's not that. Like, I mean, I don't know. It's kind of slightly complicated. But if you didn't do that, the number of places you could go would be lower growth. So it kind of restricts the growth rate if you never had that option of just like, you know, switching sides. Yeah.
I don't know. Yeah, I don't know.
Anyway,
That's a good
anyway,
one.
so,
I
yeah.
mean, I think you could get to the other option just by having very, very short edges in your graph here.
Yeah, maybe.
But I see what you're saying.
No, it has to be. Yeah, they have to match exactly. Yeah. This is actually somewhat like, you know, at least in some sense of typical
Well,
behavior. Yeah.
So then what do you think the answer is? You think that each one has some positive measure then, but
Yeah,
then
I
like,
don't
they
know.
wouldn't
No,
be
no,
measurable. or
I have to
something,
think
right?
about it. I'm just saying that, but I always
Yeah.
felt at the beginning also that this never happens. But like I don't remember, like a while ago, I thought about these problems and I decided
I think
that
it's a good
actually
question.
not so clear that this doesn't
Yeah.
happen. It might happen. In fact. Yeah.
But like if you assume that the set where you fix the degrees, the number of branch points is like measurable, which I haven't thought about, and the action's ergodic, which it is, then only one of them happens, right? Then only one number of branch points happens.
Yeah, that's right.
Do you have a guess of which number it is? I mean, how could it be something other than 1 or 2 n?
Yeah, it could be like 2 less or something, right?
Okay.
Yeah.
Okay,
Anyway,
I think it's a good question then. Or
yeah,
it is a
good question. Yeah.
Yeah, I'm essentially out of time. So we'll stop with one question. But I think it's a good one. And I think I would be very interested to see that it be less than 2n minus 3. Someone can think about that. Of course, I think what Kazar said is like the key point, that we're doing this hitting measure from a random walk, and that's like a weird measure to think about, you know, what that means in terms of just like folding together paths and graph. Okay, but thank you for your attention.
Let's thank the speaker. Okay. Any questions?
Yeah, what was question 2?
Yeah, what is question 2? Tell us
Oh,
this.
I like question 2 a lot, and I've thought a lot about it. So if you do a random walk, if you take an outer automorphism, a random outer automorphism, it's fully reducible. Okay, so it has a stretch factor, right? Any automorphism, you can define a stretch factor for it. And in the mapping class group world,